The objective of this experiment was to explore the phenomenon of oscillations and its associated properties. So what exactly are oscillations? Oscillations occur in a system where there is a regular variation in position around a central point, and this can be easily visualized in a pendulum or a playground swing as we use in this experiment. Oscillations are also present in a variety of everyday applications, from making music, like strumming the strings of a guitar, to the behavior of electrons in atoms. Other more complicated systems that utilize oscillations are mechanical devices that have an interaction of masses and elastic forces, or electrical circuits that have capacitive and inductive components. However, in this experiment, we will be using the simple model of the playground swing to demonstrate what happens to oscillations when destructive and constructive forces are applied and resonant frequency occurs.
In a system with no dampening, the oscillation of a pendulum is simple harmonic motion. We can modify the formula for a mass on a spring to find the period and frequency of an oscillating pendulum. Since frequency and period are independent of mass in a pendulum, we simply replace the k constant with freefall acceleration g divided by the pendulum length L. The resulting formulas allow us to determine the period and natural frequency for our system.
This first example shows driven oscillation as a result from constructive force being applied. In general, driven oscillations occur when an external force is applied to an oscillating object so that the object takes on the frequency of the external force. The resulting motion is then maintained so long as the same external force is continually applied, as any dampening is negated by the input of the force. A constant amplitude is observed as the object reaches the same maximum after every force applied. Data analysis further supports this, as the angle between the equilibrium point and object at its max distance remains relatively the same for each cycle observed.
The next example demonstrates destructive force. When applying this force to a conservative system, it will be slightly perturbed from a stable equilibrium point, in this case the swing. If a destructive force is applied on driven oscillations, then the amplitude of the oscillations decrease exponentially. The period of the oscillations increases and oscillations finally stop. This can be demonstrated with the values obtained from the graph. There is a linear relationship that has an opposite direction from the constructive force.
When we observe resonance in an oscillatory system, we see a much larger change in motion when compared to simple driven oscillations. This resonance is achieved when the frequency of the externally applied force matches or comes very close to the natural frequency of the system. As the frequency gets closer to the natural frequency, we will see continuing increases in the amplitude of the oscillation, with a maximum value being reached when the external force frequency matches the natural frequency. This is shown by the values recorded during our tests, which show a much larger maximum amplitude achieved. The graph representation of our data indicates a much steeper slope due to both the larger increases in amplitude as well as a larger maximum value.
As demonstrated throughout the video, external forces generate changes in the amplitude, creating variations in frequency of the system compared to the natural frequency. This new frequency is a result of the period change of the oscillation. Each external force properly demonstrates these changes by having a linear slope when graphing position against the number of applying forces. Constructive force and resonant frequency obtain a positive linear slope since the amplitude of the system rises, creating a longer period. In contrast, destructive force generated a negative linear slope due to the amplitude decreasing, creating a shorter period.